Section is going to be called energy in the atmosphere. Bless you. All right, so this starts our meteorology weather unit, and so we need to start by looking at our atmosphere. And in 5th grade, you probably talked a little bit, or hopefully at some point talked about how our Earth has a couple of different layers, these gas layers that exist over the top. The first one is called the troposphere. The second one is called the stratosphere. The third one is called the mesosphere. And the last one is called the thermosphere. And each one of these is important in some way for our Earth. Okay? The troposphere, which is the one that we are going to be spending the bulk of our time looking at, which is where weather occurs. The stratosphere, which is where the ozone layer is. The mesosphere, which is where meteors get burned up. And then the thermosphere, which is going to be where our satellites are found. Okay? So just kind of giving you a little bit of background information. And along with that, we know that Mr. or Mrs. Sun is going to strike our Earth. Okay, we know that the light from there is going to strike our Earth. And we call that a very specific name. All right, we call it the electromagnetic waves. Okay, that's a big fancy science word for something that is pretty simple to understand. Okay, all it is, it's a form of energy that travels through a vacuum of space. And really all that means is it's sun's energy traveling to Earth. Okay? The vacuum of space that they're talking about is our galaxy. Okay? So any of the planets that are in our galaxy are going to experience these electromagnetic waves. Some more than others. Okay? So if you're closer to the sun, obviously you're going to have more electromagnetic waves. All right? The other term that we need to experience is radiation. Okay? Radiation is the idea of a direct transfer of energy. So when you were doing the lab, the sand in the water, a lot of you were able to feel right underneath the light. What did you feel when your hand was right underneath the light? Emma? Okay, you felt heat. You felt the warmth that was coming on. Okay, that same thing exists when you feel sun's energy. Okay, you might have been outside before. When the sun feels warm, you just feel the warmth that's coming from the sun. And what that is it's a direct transfer of energy. Sun's energy is transferring to you. You get warmed up by the sun. Okay? So that is what radiation is. And all of this stuff is almost all energy from the sun heats our atmosphere and surface. Okay, so we get all of our energy from the sun. Okay, it's what supplies the energy for our atmosphere. It's what supplies the energy for our Earth. Okay? Now, how the radiation and the electromagnetic waves get to our Earth is important as well. So I need to draw you kind of this spectrum. All right, so it's heading in two opposite directions. And the middle part is going to be visible light. And this is the one that we are most familiar with. We can tag in the term Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Those are all the colors that you would experience when you see a spectrum of light. Okay, it's the same colors that you see when you see a rainbow. You'll see that there are reds and oranges and yellows and greens and blues and indigos and violets. Okay, and you're familiar with it because if you look outside right now, you'll see, oh, the grass is green. Oh, there goes a red cardinal flying by. Okay, and so what you're doing is you're identifying because of the fact that the visible light that we see. All right, these have what we would call as medium wavelengths. And we'll talk about wavelengths in a second. So that way you can understand what they are. So that's one way that we get radiation from the sun, all right, through visible light. Another way that we experience it is through infrared radiation. And these have long wavelengths. Okay, so they have long wavelengths. Yep.
What is that standard medium?
Wavelengths. And then over here we have what we would call as being the ultraviolet radiation. And this one is also known as UV radiation. And these have short wavelengths. Okay, so a little different here. Long wavelengths, short wavelengths. And these are the ways that we receive the electromagnetic waves from the sun. Right? So you either get them as infrared, visible, or ultraviolet. Okay, for us to understand right now. So, a wavelength. We need to figure out what a wavelength is. We know that waves travel in many different forms. Okay, we have sound waves, we have light waves, and so we have to be able to measure a wave. How far apart, bless you, how far apart the waves are from one another, how fast they're traveling. And so to measure a wavelength, what we do is we have two parts to a wave. We would say that this is the crest, the top part of the wave, the bottom part, which is called the trough. And to measure, what we do is we take the highest point of a wave to the next highest point of a wave, and that distance that's between there is called the wavelength. Okay, so to measure a wavelength, we have to take crest to crest and measure that distance that occurs. Okay, if you wanted to know the distance between this one, you'd go crest to crest. From this one, crest to crest. All right? That's how we get the wavelength. The longer the wavelength, the further the distance between the waves is. Okay? The shorter the wavelength, meaning that we have them frequent, the distance in between there is shorter. Okay, so you can see the difference between this being a shorter wavelength, this being a longer wavelength. Now that will play an effect here in a short bit. Yep.
Could you do it like for the lower ones too? Like measure it from the lowest one?
From trough to trough?
Yeah.
You could. Oftentimes, though, it's hardest to do that because when it's at its peak, it's easier to see. It's easier to measure that distance. So, can you? It depends. I would say that this going crest to crest is more of the way that a scientist would measure it. They go crest to crest. All right. So we're trying, and the other part too to that, Holden, is the fact that we're looking at the crest. We're looking at the wavelength. So this part right up here is more of the wave, and so you want to measure the wave as opposed to when it crashes down. All right, so those are the different ways, and we said that we have a couple different types. We said we have what is called an infrared radiation, and we have a UV radiation. Okay? Some of the things that they have in common with each other is that they are both not visible. Okay, we cannot see them, so neither one of them. They're different because this one has long wavelengths, and this one has short wavelengths. And the infrared is what you feel as being the warmth. Okay, so how do we experience these? This is the one that you feel that warms you up. Okay. UV radiation, on the other hand, these ones can be experienced through sunburn and potentially skin cancer. Okay? We're not really a big fan of those. Alright? We're not really a big fan of those. So, luckily, we have an atmosphere that is designed to help not allow as many of the UV radiation waves pass through. What is that layer called? Anybody remember? Yep. The ozone? It is the ozone, so it's a part of the stratosphere. So when we drew this in the very beginning, we had some of the light striking this area, which is going to be our ozone layer. And as it strikes that area, a lot of it is able to be repelled because of the fact that the ozone layer exists. Right? So a lot of it is able to strike and then be forced in the opposite direction. Okay? Some of them get through. Okay? And so that's the reason why it is suggested that you wear sunscreen, because what you're trying to do is you're trying to keep those harmful ultraviolet rays from striking your body. So that's why we wear sunscreen. All right? Anybody else know where you can get ultraviolet rays? Where else could you potentially get them? Kelly? Tanning beds. Yep. So you have to be careful with those as well. Okay? So that is the different ways that they strike our Earth. All right? And how this fits together is this. When you were young, growing up in your elementary classes, and you had drawn these nice, apparently my marker's going to stay nice and thick. That's Mr. and Mrs. Sunshine. And you didn't even know it, but what you were drawing is infrared radiation and visible light and UV radiation. You just didn't know it. You thought these little things coming off of here were nothing. They were just like the rays. But really what they are is infrared radiation, ultraviolet radiation, and visible light. Okay? Now, how does this all affect Earth? So if this is going to be Earth, if this is going to be our Earth, and we know that these light waves are going to come and pass through these different layers of our atmosphere, what is going to happen is about 50% of them are going to absorb into our Earth's surface. Okay, that means that into our oceans, into our lakes, into our ground, our land, all of that stuff is going 50% of it. Okay? And you've experienced some of these radiation waves because you might have been driving down the highway and you look and you're like, hey, look, it looks like there's water that's at the end of the road. What is that called? What is that called? Looks like there's water that's there. And as you get closer, there's no water that's there. What is that called? Begins with an M. Yep. Not mist. Yep. It's called a mirage. Okay? Because what's happening is that you're seeing the sun's radiation heating up a surface, and in return, some of the rays are being released back up into the atmosphere. Okay, so what we see is there's actually about 5% that get returned back up from the ground. Okay, you might have also seen this when you are grilling out. Okay, all of a sudden you're looking at the top of your grill, whether it's a gas grill or a charcoal grill, and you look and it looks kind of blurry. It looks kind of blurry. Why is it blurry? Because there's heat waves, there's infrared radiation that's being given off from that. Okay, so that's what is happening there. Now, we would say that because of our ozone layer, okay, imagine that this is the ozone layer, about 25% of the ultraviolet rays are returned back into this space. It's just, they strike and they get repelled away, reflected back. Okay? So 25 of them are reflected back. And we would say that about another 20% get trapped in our troposphere. Okay? Why is this important that we have about 50% that strike our Earth's surface, warm it up, and then in return we have about 20% that are striking our clouds and our troposphere and warming that up? Why is that important? Yes?
Like, you don't have to really burn back and get cold and everything to be on more safe.
Absolutely, all right? And that process is given a nice fancy scientific name called the greenhouse effect. Okay, the greenhouse effect is the idea that you are trapping heat by the gases of our atmosphere to keep Earth habitable. Okay? We like this because what Courtney had said is the fact that it allows for it not to get too cold. Even though in the winter when it's like negative 30 degrees outside and it seems like winter is never going to end, we are still able to survive because of the fact that it doesn't get super cold past the point where we can't function at all. Right? Our cars are still able to start. We're still able to keep society moving forward when it gets that cold. Now, it becomes more difficult, it surely does, but it is not at a point where we're at another planet where it's unsurvivable. All right? So the greenhouse effect is what makes Earth so unique and allows for us to be able to survive. Okay? And we haven't been able to find that in any other planet. We found water on another planet, so it means that there had to be conditions that were warm enough at one point to free it up. But we haven't been able to find one where the atmosphere is going to be able to support without having toxic gases or it getting too warm or too cold like Earth. And so the greenhouse effect is very, very, very important in terms of how we survive. Okay? And the last little thing that we need to talk about is when we do get to Earth's surface, we will notice that the sky is oftentimes blue. Okay? And again, this has to do with infrared radiation, ultraviolet radiation, and visible light. Does anybody know why the sky is blue? It's not today. By the way, that stuff that's out there, what is that stuff?
It's
Yep.
fog.
It's fog, and fog is basically just a cloud. So what happens is that anytime we learn this when we were going through the water cycle, is that if water is above 32 degrees, there is going to be some evaporation that is occurring. So there's moisture that's getting heated up, and it's because we know that when warm air gets warm, it begins to rise. And when the temperature outside is cooler, it pushes that moisture back down. And so instead of the cloud forming back up in the sky where it normally would, what's happening is the fact that the cold air pushes that moisture down, and so the cloud actually forms on the ground. And so that's what fog is, and that's what's happening. Now hopefully what's going to happen is as the day begins to warm up and the sun tries to heat up, what's going to happen is that cold air is going to begin to rise a little bit. So now the water that's in the air is going to be able to rise up a little bit as well, and eventually the fog will disappear. Okay? And so that's what the fog is. But does anybody know why we have blue sky? Why isn't it like green sky? Or why is it blue in general? Yeah. It has something to do with the atmosphere. And here's what it is. We have, what we learned, is different types of particles that exist in our atmosphere. We know that there's nitrogen that's up there. We know that there's carbon dioxide that's up there. We know that there's oxygen up there. We know there's dust, there's smoke. There's all kinds of different particles that exist in our atmosphere. Okay, gas particles that exist. And what we do know is the fact that the sun is going to strike our atmosphere at different angles. Okay? If we look at the globe for a second, and the Earth is constantly turning, okay, what does this result in when it's constantly turning? What does it produce? Yeah, take a shot. Okay, it does produce sunlight, but what does this produce by the spinning of the Earth? Yep. It does with the tilt on the axis, but not yet. We're still not at that point. Yep, Emma? Not the seasons. That's with the tilt of the axis also. Yep.
Gravity?
Not gravity. I mean, it does. It does. I will say it does help with gravity. Yeah, it's a key component with it. Yeah. Not yet. Not yet. No. Good try. All right. So let's think about this for a second. If this is where North America is, right here, this is where we are. Okay. If my face is the sun and it's constantly turning, what is it producing? Day and night. Very good. Okay. It takes about 24 hours to make one complete turn. All right. So this is constantly in motion. Also, we know that, by the way, is the sun going around the Earth or is the Earth going around the sun? Yep. Okay, the Earth's going around the sun. So if my face is the sun, okay, what does this result in? When it makes one revolution all the way around. President Reagan. Okay, it makes a year. How long is a year? Yeah. 365 days plus, yep. No, yep. Okay, yep, and a quarter. So it's 365.25 days. Well, Mr. B, we don't have 366 days in a year. No, we don't. We have 365 days in a year. And so we have 0.25, 0.25, 0.25, 0.25, which equals one whole. That's why every fourth year we have the leap year. We add on an extra day because it takes 365.25 days to actually the Earth to make one complete revolution around the sun. So that's great. That's wonderful. But here is where North America is. This is where we're located. So right now it's dark, and when it first starts to turn, by the way, where does the sun rise in which coast?
The west.
East. Rises in the east. Okay, so here we go. It's starting to, it looks like the sun's coming up. And so it looks like Mr. or Mrs. Sunshine is doing one of these things. Okay, I'm just going to symbolize it by that. Looks like it's doing one of these, right? That's what it looks like the sun does. And to some degree, to us, that's what it does. But in reality, it's just the Earth is turning. And so when the sun first begins to come up, what color is the sky oftentimes when it's sunrise or at sunset? What colors do we notice? Yeah. Pink. We notice that there's some pink. Okay, so let's choose some pink. Usually it's a brighter pink, but yeah. Okay, what else?
Orange.
Orange. Okay, so let's add in some orange. Okay, what else? Yeah. Yep.
Yellow.
Okay, we see that there is some yellow. Okay, yeah.
Red.
Okay, usually some red, and you could go on with a couple other things. So why is it that at sunrise and sunset that the color is oftentimes these yellows, reds, oranges, pinks colors? Yes?
Because the sun is somewhat of that color?
Okay, not because of that. Yep. Oh, interesting. We got to go back to our dear friend Roy. Okay, if you remember my dear friend Roy. Okay, Roy is located right here. What colors do you notice that are that make up Roy? Yep. Red, orange, and yellow. Pretty close to the same colors that you just told me right here. Now, look at what we have in terms of wavelength. Is red, orange, yellow closer to long wavelengths or short wavelengths? Just say it aloud. Long. Which means that when the sun is first starting to strike our surface, when it begins to turn, it has a long way to strike these particles and reflect them back to us on Earth. And because of the fact that those are those long particles, we see colors that fit into the Roy part of the spectrum. And as it looks like the sun begins to come up higher, the wavelength begins to shorten down. Now, it never gets close enough to be this region right in here, the indigo violet, okay, because of the angle, but it does get close enough to reach and hit the blue, okay? And so what we see is the reason why the sky is blue is because we've shortened down the wavelength. We've shortened down the wavelength that exists now between the Earth and those particles and the reflection that needs to occur. What happens at the end of the day? Sun begins to look like it's going down in the horizon as Earth turns away. Again, now the angle becomes long again, and it is the reflection that we see. This process is known as scattering. Okay, so scattering is taking dust and gas particles being reflected by the wavelength of the sun. Okay, so we start to see that Earth gets its energy through infrared, ultraviolet, and visible light. All of those contribute to heating up Earth's surface to allow it to be, us to be able to survive on it. And also it helps to give us the sky the color that is needed. And that is it for notes.